This is the final video for the series in parallel circuits unit. And in this one, we're just going to work through a couple of circuits here. What these are circuits that combine parallel and series. And really what we want to be able to do is we want to find the voltage drop across every single resistor, and we want to find the current in every single wire, and we want to calculate how much power each resistor consumes. So, getting us started here, let's take a look at this first circuit. When I look at this, the first thing I do is I draw out the path of all of the currents. So I have a current that's leaving my power supply. It's a 24 volt power supply. That current travels up here, and when this current encounters this first junction, it's going to split up. So let's say I have an I1 going through resistor R1, and let's say I have an I2 going through resistor R2. These currents then combine to form my main current I. Then it breaks again, and I'll call this an I3 and I4. It will combine then, and I'll have my main current I returning to the battery. Now this has to be like this because we have conservation of charge, and current goes along with charge. So I see that I need to calculate 5 different currents. The next thing I do is I start to think about voltage. Now R1 and R2, if we look at these, well, they're parallel, so they're going to have the same voltage across them. So I'm going to call this a VP1, voltage for parallel 1. And that voltage, whatever VP is, it's going to be the same across R1 and R2. Likewise for R3 and R4, I'll call this VP2. They will have the same voltage across them as well. And I hope you notice that VP1 plus VP2 should add up to give us 24. Okay, so let's make our table. I've got 4 resistors. All right, so we got R1, which was 100 ohms. We have R2, which was 250 ohms. R3, which was 350. And R4, which was 200 ohms. All right. So we got our table set up. Now we need to calculate the equivalent resistance. Well, as I see here, I've got 2 branches that are in series with each other, and parallel is 1 over plus 1 over. So this equivalent resistance, if I were just to write this out, it would be 1 over 100 plus 1 over 250. Got to remember to invert that. Plus 1 over 350 plus 1 over 200. And we got to remember to invert that. So this equivalent resistance would equal 71.42 ohms plus 127.27 ohms, or just simply 198. Now, I went ahead and I found, if I were to give these names, I might call this, like an RP1 and RP2 for parallel, because there's two sets of parallel resistors. Now that I have the equivalent resistance, I can calculate the current, my main current I. And now that I have my main current I can calculate that VP1 and VP2. I'm just using Ohm's law, V equals IR. And, for VP1, we have a current of I going through it. And the resistance of this first, this first branch right here, we found that to be 71.42. So I can calculate that voltage drop just across those branches. So for the voltages in our table down here, for R1 and R2, the voltage will be 8.57 volts. And for R3 and R4, the voltage will be 15.27. And notice that 8.57 plus 15.27 comes really close to 24. Now for the current. Well, current is just voltage divided by resistance. So what I can do is I can take my voltage divided by my resistors to calculate those individual currents. So for this first one, I just do 8.57 divided by 100, and then 8.57 divided by 250, then 15.27 divided by 350, then 15.27 divided by 200. And, these two right here should add up to give me my 0.12 amps, and then these two should add up to give me my 0.12 amps. Finally, for power is just current times voltage. So I just take my 0.0857 times 8.57, my 0.0343 times 8.57. I just go down through and I just multiply them. So that's basically it. I can do some checks. For example, the total power this circuit uses would be 24 volts times 0.12 amps, which gives me 2.88 watts. And then if I go through and add all these together, I get something very, very close to 2.88 watts. So everything seems to work out fine. So that's the first circuit. And notice what we've done is we've calculated the voltage drops across each resistor. We have found the current in every single wire, and we have calculated the power consumed by each resistor. Let's take a look at another one. This is another example. This one looks a little different. A lot of people get this confused. They would see R1, R2, and R4 as being in series. So they would do 20 plus 30 plus 20. But you can't do that. Notice that up here we have a node or a junction, and we have a junction down here. So really what's happening is I have R1 being in series with some parallel resistors being in series with R4. So what will help you figure this out is if the very first thing you do is if you draw out where the currents are going. So I have my main current coming out of my battery. It's traveling along here. And when my current encounters this node, it will split into two other currents. I'll call this one I1 and I2. Now notice my I1 is going through R2 and my I2 is going through R3. The numbers don't have to match up like they did in the previous example. These currents then will recombine to form my main current I, which returns to the battery. So if I were to look at this then, now if I do my voltages, I would have, let's say, a V1 across R1. Let's say I have a VP for parallel across this junction. And let's say I have a V2 across that resistor. So R2 and R3 would see the same voltage drop across them. And then V1 plus VP plus V2 better add up to give me 10. All right, let's go ahead and make our table then. So R1 is 20 ohms. R2 is 30 ohms. R3 is 50. And R4 is 20. Okay, now that we have our table, what we want to do next is calculate the equivalent resistance. So that's going to be 20 plus, and then I've got 1 over 30 plus 1 over 50. Make sure you invert that, plus 20. So really my equivalent resistance will be 20 plus 18.75 plus 20, or 58.75 ohms. And this 18.75, I'm going to label that RP because that's the parallel resistance for R2 and R3. Now we can go ahead and calculate our main current. So that's going to be 10 volts divided by 58.75 ohms, or 0.17 amps. Now, immediately I can start putting things in my table. That means going through R1, I have a current of 0.17 amps, and going through R4, 0.17 amps. So I can go and put those in my table. Now, what I can do is I can start to calculate my voltage drops. V equals IR. So for R1, it's just going to be 20 times 0.17. So that's 3.4 volts. And then I get the same thing across R4. For the voltage across R2 and R3, again, that's my VP, that would equal I times RP. So that's going to be my 0.17 amps times 18.75 ohms. So that gives me 3.19 volts. Once I have those volts, remember that current is volts divided by resistance. So 3.19 divided by 30, that gives me real close to 0.1 amps, or 0.11 amps. And 3.19 divided by 50 gives me my 0.06. Now, these two, across R2 and R3, those had better add up to give me my 0.17, which we can see that they do. Finally, power. It is current times voltage, so I just take my 0.17 times 3.4. I just fill up the rest of the table. If I wanted to, I can calculate my total power consumed. So 1.7 watts, and if I added together these four powers, I would get something very close to 1.7 watts. This last resistor, we're not going to work it out. It's not part of our learning goals. But I want you to recognize that it is possible to have a circuit with two power supplies in them. And if you're curious, you can find a number of videos on YouTube which would help you solve something like this. That concludes this unit's worth of notes.